All right, so let's look at example 1. Find the equation of the tangent of the curve at y equals x cubed minus 2x squared minus 3 at the point where x equals -1. So if we need a tangent line, it means we need a line that fits the form y equals mx plus c. I need a gradient and a point the line goes through. So if we're interested in x equal to -1, if I substitute -1 into the equation, I'll get y equals -6. So there's my point. Now I need a gradient. To get a gradient, I get the derivative. So dy dx is 3x squared minus 4x at x equal to -1. I substitute that in, and I get 7. So the gradient of my tangent line is equal to 7. Okay? So I know the general form of a straight line, y minus y1 equals mx minus x1, or just y equals mx plus c. Substitute your point in. So y minus 6 equals 7 times x minus 1. Just a little bit of algebra in there, take our 6 across, and we'll get the tangent line, which I like to write yt for y tangent subscript, or y subscript n for normal, is equal to 7x plus 1. Obviously, if we just use our CAS feature, we get our 7x plus 1 there. Okay, so continuing in the same vein, if I'm looking for a normal line, well, I need to make use of the relationship that the gradient of the tangent times the gradient of the normal equals -1. In other words, the gradient of the normal is -1 over the gradient of the tangent. So I still need a point the line goes through, because a normal line is still a y equals mx plus c line. And I need a gradient that the line goes through. So if I'm interested in the point x equal to a half, if I substitute x equal to a half into that equation, work my way through it, I end up with y is equal to 0. So the coordinate I'm interested in is the point a half, 0. Now I've got the point, I need a derivative for the gradient. So the derivative of that gradient is 4x minus 3. At x equal to half, I get m equal to -1. So the tangent line has a gradient of -1. So the normal line is -1 over that, which is +1. So I want to work out the equation of a straight line that has a gradient of 1 that goes through the point half, 0. Substitute that in, I get the y normal equals x minus a half, which again is what our calculator dump gives us. All right. So let's look at a few more involved examples now. Actually, I think this is a question from the exercise, question 17. I need to find the tangent of the curve with the equation f of x equals x cubed plus x at the point a cubed plus a. So I guess it's important to note that this coordinate a cubed plus a we get if we substitute x equal to a in. Passes through the point 1, 1, find the values of a. So again, I need a tangent line that happens to pass through the point 1, 1. So the tangent line at x equal to a, let's find that equation first. So I've got the point it goes through already, it's been listed, so I want to find the tangent line, so I need to know what dy dx is. So dy dx is 3x squared plus 1, and at x equal to a, the gradient of that tangent line is 3a squared plus 1. So if I set up y minus y1 equals m, x minus x1, and put the y and the x values in, it's probably just as easy at this point, instead of manipulating, I put the point 1, 1, because it's got to satisfy. That's the rule for my equation there. So that's my tangent line there. It's just not organized or structured in a way to simplify things. But if I put the point 1, 1 in, it just gives me a couple of less variables to deal with. So if I substitute the point x equal to 1, y equal to 1, I get 1 minus a cubed minus a equals 3a squared plus 1 times 1 minus a. Carefully expand all the brackets. So 3a squared times 1, 3a squared times minus a, 1 times 1, 1 times negative a. And then we get a couple of values cancel out there to leave me with 2a cubed minus 3a squared is equal to 0. I want to find the a value that makes that true, so I've got to factorise that. If I take an a squared out the front, I get 2a minus 3 equal to 0. And so then my two solutions are at a equal to 0 and a equal to 3 on 2. My CAS, find the tangent line of that function there at the point a, and there's the equation of the tangent line. And I want to solve for a, just undo that highlight, substituting in y equal to 1, x equal to 1, and it gives me my 0, 3 on 2. Okay, so there's a few examples in this set. Let's have a look at the next couple. I need to find a normal, a normal to the equation y equals root x has equation. So there's the equation of my normal, where a is a real constant, find the value of a. So how do I find the equation of a normal? Okay, I need to find a gradient and a point that the line goes through. So first things first, let's find the gradient. dy dx is equal to half x to the minus a half, which is 1 over 2 root x. So I need to find, so the gradient of my normal is -4, so the gradient of my tangent is 1/4. So I'm trying to find the point that we're interested in here. So, because if I'm to do a quick sketch of this, I'll undo that. Let's visualize what it is we're trying to work out. I've got the square root of x, and I've got an equation -4x plus a. So that might look something like that. Yeah, that's the normal line. What I'm trying to find now is, well, what tangent line does that correspond to? So I need to find that point there. And that way I can find a y-intercept. So I'm trying to find the coordinate. So if I solve 1 over 2 root x equal to 1/4, I'll get x is equal to 4. And if I put x equal to 4 into the equation y equals root x, I get y equal to 2. So what that enables me to work out is that the point that my normal line goes through is the point 2, 4. So 2, 4 has to satisfy the equation of that normal line that I've been given. So if I substitute that 2, 4 into the normal line, I'll get a is equal to 8e, which seems feasible. You know, it's a big positive y-intercept. All right, so it's the same process. I guess the trigger clues, normals. If you're finding a normal to an equation, we're going to need gradients. If we need gradients, we're going to need to find our derivative. Okay, 2D. The graph of y equals x minus 1 squared times x minus a is shown on the right. So there's the graph of it. Find the exact value of a such that the local minimum at the point A lies on the line with equation y equals minus 4x. So, in other words, y equals -4x has to go through the point A, which is the local minimum. All right, so let's try and find that point A. So let's work out dy dx. Now, it could quite feasibly be a CAS question, this one, because the algebra gets a little bit messy, but let's have a look. So dy dx, a little bit of a chain rule, derivative of the first, which is 2x minus 1 times the derivative of, times the second, plus the derivative of the second, which is just 1, times the first. Let's take that x minus 1 out as a common factor. And I end up with x minus 1, 3x minus 2a minus 1. Okay, so if I solve that equal to 0, I get stationary points at x equal to 1 and 2a plus 1 on 3. So x equal to 1 is clearly the first stationary point that we've got on the graph, and which makes 2a plus 1 on 3 the point at A. So what's the coordinate of the point A? Well, if I substitute 2a plus 1 on 3 into x minus 1 all squared x minus a, which is what I've done there. So that's my x minus 1 all squared x minus a. So minus 1, I'm going to make it 3 on 3. So I end up with 2a minus 2 on 3 all squared. Minus a, make it negative 3a on 3, get a common denominator. So 2a minus 3a is minus a plus 1 on 3. If I take the 2 inside the bracket out, don't forget that's 2 squared. So that's where that 2 squared comes from, and leaves me with an a minus 1 squared on 9, because I've done the same thing to the 3. So I take 3 squared outside the bracket, times a negative out the front to make that an a minus 1 as well. And that way I can get a minus 1 cubed, negative sign out the front there, and we get our 4 over 3 times 9, which is 27. So it's not impossible algebra, but it's challenging. So what we found is we found the coordinate of that point. Okay, and the coordinate of that point is 2a plus 1 on 3 comma, negative 4a minus 1 all cubed on 27. I could have found out the y value here by also substituting into y equals negative 4x, because it also goes through that coordinate. So there's my, because the y equals negative 4x goes through the turning point, negative 4 times x, okay, which is negative 8a minus 4 on 3. So the two y values have to be the same. That has to equal negative 4 over a minus 1 all cubed on 27. So if I've got a line in there from nowhere. So if I take the 27 across, 27 on 3 becomes 9. So I could expand the left-hand side to get negative 7 to a minus 36. Negative 4 times a minus 1 all cubed. There's my cubic expansion there. Group all my terms together. Divide everything by 4 since it's a common factor. And then factorize that. So negative 2 is a 0 of that. So I've used synthetic division. Obviously, we could use our any division that you wanted to. In reality, we're probably going to use CAS, but that's okay. So negative 2, so I get factors of x minus 2. Sorry, x plus 2. Negative 2 is a solution, so x plus 2 is a factor. And x squared minus 5x minus 5 is my other quadratic factor. So if I solve that quadratic factor equal to 0 by completing the square, I get x equals 5 on 2 plus or minus 3 root 5 on 2. And since I'm looking for my x coordinate, which is greater than 1, the a value greater than 1, I'm going to take 5 on 2 plus 3 root 5 on 2. All right. If we're going to use our technology, which is likely, we just got to keep things structured. We want to find the derivative of the equation, solve that equation equal to 0, and there's my two stationary points. All right. Substitute 2a plus 1 into that equation, and that gives me the y value. So then I want to equate the two y values. That's the y value by substituting it into the cubic. There's the y value by substituting into negative 4x. And then my calculator gives me my solutions. And then obviously you look at your solutions, see which ones fit the conditions. Since a had to be greater than 1, there's only one of those that does that. All right. Find the equations of the straight lines that pass through the point 1, negative 2, and are a tangent to the parabola with equation y equals x squared. So I thought I might do a diagram here. I think diagrams help us just to get a picture of what it is we're looking for. So if I've got the point 1, 2, you can see the red parabola there at y equals x squared. I'm trying to find those two coordinates at x2, y2, and x1, y1. All right, and I know that they're tangent lines. So tangent lines means at x equal to x1, the gradient at that point is the same as the gradient of the line. So let's just pick point. I guess the first thing to realize, let's undo, is that these are the points P, x squared, yeah? Whatever the x value you put in, the corresponding y value is just x squared because that's the function. So let's think about our gradient of the line. Let's get the gradient of the line joining those 2 points, those green dotted lines. It's just y2 minus y1 over x2 minus x1, which is x squared minus 2 over x minus 1, which is x squared plus 2 over x minus 1. That's the gradient of the line. Well, what is the gradient of the line at the point? That's what dy dx is. So dy dx is equal to 2x at the point x. So the gradient at that point is just 2x. So those two gradients are going to equal each other. So the gradient of the line by using y2 minus y1 over x2 minus x1 is the gradient at the point by using the derivative. So really what we're going to do is just solve both of those. Multiply the x minus 1 across, expand that bracket, group the terms together. Factorize. I'm a bit of a completing the square fan. You could use a quadratic formula, but if you get used to completing the square, halve the middle term and square it. Plus 1 minus 1. So minus 1 minus 2 is minus 3. X minus 2 all squared. I get x is equal to 1 plus or minus root 3. All right? So that means that that's the x coordinate of the point that we're interested in. 1 plus root 3 up there at x1, 1 minus root 3 down there at x2. All right, so if that's the point we're interested in, I need to find the gradient of the line at that point. So the gradient of the line is given by y equals 2x, which is the simpler way to do it. So the tangent line of line 1, mt1, is just 2 times 1 plus root 3. The tangent line mt2 is 2 times 1 minus root 3. So there's my two tangent lines, all right? What about the coordinates that the point goes through? So if y is equal to 1 plus root 3 squared, because y is equal to x squared, the y coordinate is 4 plus 2 root 3. Similarly, if the x value is 1 minus root 3 all squared, the y coordinate is 4 minus 2 root 3. So now I've got two lines to find out. I've got gradients, two slightly different gradients, two slightly different points. Y minus y1 equals mx minus x1, or y equals mx plus c. So if I find out the first point, I get y minus y1, 4 minus 2 root 3, is equal to m, 2 times 1 plus root 3, times x minus x1. So really it's just now an exercise on a bit of algebra and keeping track of your coordinates. 2 times 1 plus root 3 times x is, I'll multiply the 2 in, so there's my gradient. 2 times 1 plus root 3 times negative 1 plus root 3. Expand every term, 4 terms. Yeah, so I get 2 times negative 1, 2 times root 3, 2 root 3 times negative 1, 2 root 3 times root 3. And then bring that y value across to the right-hand side, which will give me a 4 plus 2 root 3. So if I group the terms together, my 2 plus 2 root 3 x term doesn't change, but my y-intercept of negative 4 minus 2 root 3. All right, so let's repeat the same process now, except we're going to use the second coordinate, which is x equal to 1 minus root 3, y equal to 4 minus 2 root 3. Okay. Again, substitute my values in. So there's my 2 root 3 x expanding. 2 times negative 1 is negative 2. 2 times negative root 3, minus a minus in there, is plus 2 root 3. Negative 2 root 3 times negative 1 is positive 2 root 3. Negative 2 root 3 times positive root 3 is negative 2 root 3 times root 3. Negative 2 root 9, which gives me a minus 6. Group my terms together. There's my mx term, which doesn't change. And I get a minus 4 plus 2 root 3. All right. So again, I guess that a challenging setup, the numeric calculation side of it can be a little bit tricky. Typical exam 1 question? No, not really. Challenging exam 2 question perhaps, where you'd be expected to show all the working out. All right, near the end. We've got a function here, x squared e to the minus a half x. Show that the point on the graph where x equals to an equation of the tangent is. I need the equation of the tangent. So at x equal to 2, y is equal to 2 squared times e to the minus 1, which is just 4 e to the minus 1, which is 4 on e. So there's my coordinate. Let's find the gradient, dy dx, derivative of the first times the second, plus derivative of the second times the first. Let's get that e to the half x. In fact, an x e to the half x is a common factor out the front, and leave me with 2 minus a half x. Just try to get in the habit of getting that common factor out the front. In particular, at x equal to 2, which is the point of interest, dy dx is equal to 2 on e. I've got the point we've already spoken about. Substitute that into the rule, y minus y1 equals mx minus x1. Expand this expression. I end up with 2x on e minus 4 on e. Bring the 4 on e across from the left-hand side, and we get our y equals 2 on e to the x, which is what we had to show. What about if we are interested in the equation of the tangent at the point 0, 0? So if I put x equal to 0 into the derivative, I just get 0 times everything, which is just 0. So the gradient of that point is 0. So it's a horizontal line that goes through the point 0, 0. Now, show that these are the only two tangents that pass through the origin. Okay, obviously we've got our calculator dumps there, tangent line, just to show how we can use the CAS feature if we've got calculator available to us. All right, so instead of picking two specific points and getting the equations, what I want to do now is just pick any generic point and then have a look at the y-intercept. What we want to be able to do is look at for any generic tangent line, that y-intercept is meant to be equal to 0 only if a is equal to 0 or 2. So let's get the generic tangent line. We've got dy dx. I'm just going to put a point x equal to a. It's a pretty bad a, but it's an a. So dy dx is a e to the half a, 2 minus 2, 2 minus a half a. And if I put x equal to a into the function y, I get a squared e to the minus half a. So there's my tangent line. Y minus y1 equals m value, times x minus x1. Probably should both be round brackets there, so whoops. Just to keep it consistent, or both square, it's up to me. Now we need to show that the y-intercept is equal to 0 for our two cases, for the two cases we've been given. So what's our y-intercept in this case? So the y-intercept is, well, it's there's the m value there. Okay, so that's m times negative a, which is why I've now got a negative a squared out the front. So negative a times the m value is negative a squared e to the minus a half a, plus the expression from the left-hand side that comes across. That's the y2 term. So what does that mean? I'm going to expand out this bracket here. Or actually, I'm going to take e to the minus a half, a squared e to the minus a half a out the front as a common factor. Easier, because that leaves me then with a minus 2 plus a, if I multiply that a through, and plus 1, which is that expression. Okay, so minus 2 plus a half a here is this expression in here, but we've got a negative sign there because we had a negative out the front. So if I simplify the bracket inside, I end up with a half a minus 1. So that's my y-intercept. When does that y-intercept equal to 0? Well, it's a product of terms, null factor law. So it's only equal to 0 if the first term is equal to 0 or the second term is equal to 0. Since the first term is an exponential function, it's only going to be equal to 0 if the term at the front is 0, which is the a squared term. So if a is equal to 0, it'll equal 0. If I solve that expression there, a half a minus 1 equal to 0, I get a equal to 2. So the only time the y-intercept is equal to 0 is when a is equal to half or a is equal to 2, which is what we had to show. Again, on the calculator, let's work out the tangent line to this function at some point x equal to a. So there's the equation of the tangent line. That's my x there, so there's my mx. So here is the y-intercept. So if I solve that y-intercept equal to 0, I get a is equal to 0, a is equal to 2. So I guess the key with these sorts of questions is not to be thrown out by the fact that there's no numbers in them. We've got all this generic a or b or k term. Yeah, just keep track of what each term is represented by and what you're trying to show. All right, just about there. The diagram shows the curve whose equation is given by that quartic and the normal to the curve at the point A. where x is equal to 1. I need to show that that normal is y equals x minus 3 on 2. So I'm trying to find the equation of that blue line at x equal to 1. So at x equal to 1, f of 1 is equal to negative a half. So the point I'm interested in is the point 1 negative a half. So there's the point. I now need a gradient. dy dx is given by, just differentiate. I'm interested at the point where x is equal to 1 specifically. So at x equal to 1, I get f dash of x is equal to negative 1, which means the gradient of the tangent line at negative 1 is, at x equal to 1 is negative 1. So the gradient of the normal line, negative 1 over negative 1, which gives me positive 1. So I've got a point and a gradient, y minus y1 equals mx minus x1, and we get our x minus 3 on 2. Okay, now show that this normal is a tangent to the curve at a point B and find the exact value of the coordinates of B. So this line of y equals x minus 3 on 2 now has to be a tangent line to the curve, which means the gradient of that line, y equals x minus 2, is 1. So at some x equal to B or x equal to A or whatever we want to put, some f dash of x, the gradient of the line is going to be equal to positive 1. So there's my derivative again. I'm going to multiply the 2 across and bring it back to the left-hand side. And there's my quartic that I need to solve equal to 0. So again, if I put negative 1 into the equation, I get a 0. I'm going to use the synthetic. We could factorize it any way we wanted to. But just when there's no coefficients anywhere, I find synthetic really easy. I get 8x squared minus 11x plus 1. Solve that equal to 0. And I get, and I went for the quadratic formula here instead of completing the square because it would have been messier. So minus b plus or minus b squared minus 4ac over 2a gives me 11 plus or minus root 79 on 16. Now, both of these solutions are greater than 0. So that means the only solution that is to the left-hand side is where x is equal to negative 1. Okay, which is the first one I found. So fortunately enough, I'm not looking to substitute any of those messy expressions in. I just want to substitute negative 1 into the equation. If I put negative 1 into the function, I get negative 5 on 2. So we're saying that the coordinates of B is negative 1, 5 on 2, negative 5 on 2, which seems reasonable. We've got a graph there and looks like it's a reasonable answer. Righto, done. Off you go.